Okay, today we're going to look at section 2.5, solving exponential equations and log equations. So here's how we go about doing that. Solving equations. So, exponentials. Exponential equations, they're going to be, what you do is you look at it a couple of different ways. The first one is it of the form b to the x equals b to the y? If that is the case, then we can just simply rewrite it as the exponents must be equal also. This represents what's called a one-to-one. And the goal here is I have to get this expression to be a power of some base, and this side has to be a power of the same base. That's how this property here works. And then after I show you all those processes here that we're going to follow, I'll give you some examples of each one. Actually, let's go ahead and do it now. So here's an example illustrating this. 3 to the x times 3 to the negative 3x minus 2 equals 1. So can I get this equation to look something like that? That's what you're looking for. And if the answer is yes, then we do so. And if the answer is no, then we will go to the next process. So to do that, I have to get a base number to a power. That means I have to use exponent rules to get this to be 3 to some power only. Since I am multiplying numbers of the same base, I simply add the exponents. So this becomes 3 to that plus that, which gives me a negative 2x minus 2. Now, for this property up here, this process to work, this side has to be a power of 3 also. So is there a way I can make 1 into 3 to a power? And the answer is yes. Just make it a 0. Now I have this equation in that form. And so by the one-to-one property, if this is true, then the exponents must be equal. So then I can just write negative 2x minus 2 equals 0. And then to solve this simple equation right here. Add the 2, divide by negative 2, and you get x equals negative 1. Now, once you solve an equation, it's important that you always check to make sure that it's true by plugging this back into the original equation and making sure that you get the right answer. That is indeed the right answer. In the solving of these equations, you're going to get what's called an extraneous solution. Extraneous solution. For the most part, I mean, the definition we'll use for this one is just basically a false answer. So when you solve it and you get x equals a number, then you try and plug it in, it won't work. This is an extraneous solution. And if it doesn't work when you plug it in, this is why you got to check, then you just X it out. You don't circle it. That does not count as a solution. In this particular one, it will work. And so let's look at what happens if you can't put it in that form. Okay? Well, before you do that, little side things here. If you have more than one exponential, we want to set the whole thing equal to 0. To 0. Or we want to try factoring and or the quadratic formula. Now, I'll show you one of those that will come a little bit later. Once I have this thing in an equation that doesn't fit one of these up here, then I want to isolate the exponential. Once I've isolated the exponential, then I'm going to use, basically what I'm doing is I'm going to change forms. Okay, you want to change forms, and you're going to use box, circle, triangle to help you change forms. Once you've done that, solve for the variable. And the last one is check for extremes. Okay, this is what we're going to be doing. I'm going to give you some examples now for exponential solvings that represent how to go about doing all this. So here's an example that you cannot put into the one-to-one format. So because of this plus sign, I can move this over here, okay? And when I do, you'll see that 6 to this over here, and then subtract the 6 from this side over here, gives me 45, hopefully. I can't make this a power of 16. It's just not going to happen. So to solve this, to get to this exponent up here, I need to change the form of this using the box, circle, triangle. To get up into the exponent, we got to get this into a log, because the log is the exponent. And so how do I do that? Well, this is the base number, the box. That's the circle, that's the triangle. And so we just change our form. This will be a log base 16 of 45 must be equal to that exponent. That's how it works. Solve for this variable by adding 3 to both sides. So now I have 3 plus the log base 16 of 45 equals x. And that is your solution. But it doesn't really make too much sense to us. So what we usually do is we just give an approximation of that and round it to 3 decimal places. When you do your work for me, I want to see the actual answer and the decimal approximation. So you just type this into your calculator. I'll show you this one. Oops, let's turn it off. Let's try and get it so there's no glare. So you just type in as you see it. The log button's sitting right over here. So I have 3 plus the log base 16 of 45. Control Enter to give the decimal representation, and then just take that number and round it off to 3 decimal places. So 4.373. And so that's what I'll be looking for in doing your work here. Here's another example. In this example right here, you're going to see it looks a little weird. And what you see here is I have multiple, more than one exponential. So if I have more than one in that case, I said to set it equal to 0, which it already is. And then I need to try something to make this easier. And what I can notice here is that this falls into a quadratic equation format. It looks, if I take this thing right here, then I can write this and I call that a. So if I say a is e to the x, then I can rewrite this as a squared minus 4a minus 5 equals 0. A simple quadratic. And then how do I solve a quadratic? I can either try and factor it, or I can use the quadratic formula if I can't factor it. So if this factors into this, then I can then transfer this process over here to the e to the x, and this factors into e to the x minus 5 times e to the x plus 1 equals 0. And so just like in algebra 1 and algebra 2, we have a product that's equal to 0. So then each of these can be equal to 0. Solving, now you have 2 problems you need to solve. So this becomes e to the x equals 5, e to the x equals negative 1. And then now we have 2 problems that we solve. To get to the exponent, you got to change its form. Base e is the natural log. So it'll be log base e of 5. So the natural log of 5 equals x. And this one over here, the natural log of -1 equals x. And then we use our calculator, that's what the solution is, and we can do an approximation for it. And in doing so, you will hopefully notice something. So the natural log button is sitting right here. So the natural log of 5 is this. So x is approximately 1.609. And then the natural log of -1. Oh, and we get an error. Now, we kind of knew it was going to happen up here, but if you didn't recognize it, I have an error here. So what does this mean? Why do I have an error here? Well, remember, the e to the x graph, real quickly, is this graph. And it has a horizontal asymptote at y equals 0. So is there a value of x that will make this answer a -1? No, because this graph does not go below the x-axis. So there is no answer that makes this happen. This right here is a no solution response. So you would check this out, you would plug this in, make sure it works. It will. I'm starting to save some time. And so then you would circle your answer. So that's how I can do one that has multiple things in it like that for exponentials. Now, I'm going to switch over to the log type equations. So what are the rules for log equations? Well, the same process. I'm just going to list them all and then we'll do some examples of it. First thing you would look is the one-to-one aspect. Is it of the form log base b of x equals log base b of y? If it is, and I can get that to happen, then I can simply just make this equal to x equals y then. So our first look is to see if I can make that happen. What if I can't? Well, then I look and see if I have more than one log, you need to use the condensing rules. Remember, if I can't do this, then I need to use condensing rules to condense it down to a single log where I can then isolate the log. And I'm isolating the log in preparation to use the box circle triangle. In this case, though, I'm using it from the log perspective, so I'll have something like this. An isolated log, and then I put it into this format over here so that I can solve it. Once I do this, solve for the variable. And then the last one, and especially for logs, definitely check for extraneous solutions. They occur more often here than the exponential ones. So that's what we're going to be doing here. Let's look at some examples. So real quickly, here is what a one-to-one would look like. The natural log of 5r minus 3 equals the natural log of 4r plus 6. They are of the same base. Both are natural logs. That means they are both base e. I have them equal to each other. It is classically one of those. So then all I have to do is just take the two arguments, 5r minus 3, and that must be equal to 4r plus 6, and then solve this out. So minus the 4, add the 3, and I end up with r equals 9. When you do extraneous, you should plug it in and work it out, make sure it's true. A quick check for extraneous is simply this. Remember, the natural log are all logs. This argument has to be, when I plug this number in, that number has to be greater than 0. So if I plug this number in and I get 0 or a negative, then I know that that number will produce an extraneous solution. And you just cross it out, don't circle it, and then circle whichever one you have a solution. It is possible to have more than one answer. It is possible to have no answers. So you always need to check all of your work. Once you're done, you can circle it and you're good to go. Here's another example. Log base 2, x minus 10, minus 6 equals negative 5. So in this case, I don't have two logs, so this can't be one-to-one. I have a single log, so I want to isolate the log. So that means anything that's being multiplied or added to this log, and this is the log right here, that whole thing. Anything that's being added or multiplied to that needs to be moved to the other side using operations. So I end up with log base 2 of x minus 10. Add the 6 gives me a 1. Once I have isolated it and it's equal to a number, then it is of this form right here. So to solve it, you change it to that form right there. That's the base number, that's the exponent, that's the triangle part. So I end up with 2 to the 1 is x minus 10. Solving for x, 12 equals x. Now I'll check it. If I take the 12 and I plug it in there, I'm going to get 12 minus 10, which is 2. Log base 2 of 2 is 1. 1 minus 6 is negative 5. That is indeed going to work, and that is my solution. Let's look at some other ones. What if I have more than one log? Well, if this number over here was a 0, then I could easily move that over and I would have a 1-to-1. But because I have a 2 here, it is not going to be, I can't put it into a 1-to-1 format. So I have more than one log. If I have more than one log, I need to condense the logs using the condensing rules, into a single log. So I have this rule, if you don't remember it, and we had the u times v was log base a of u plus the log base a of v. I have this, I need to write it like that as a product. So this becomes the log base 9 of x times x plus 24. Doesn't matter what this is in here. I now have an isolated single log that I can then use the box, circle, triangle. So that's the box, that's the circle. So I have 9 squared is x times x plus 24. Now at this point, to solve this, you're going to need to distribute. You'll see if you have a quadratic. And to solve quadratics, everything has to go to the same side, equal to 0. So multiplying and moving things around, this becomes x squared plus 24x minus 81 equals 0. And at this point, you're either going to factor or you're going to use the quadratic formula. Can I find factors of 81 that will try and give me 24? And 27 and 3 will work. So when I solve each individual one, this one right here, x plus 27 equals 0, or x minus 3 equals 0, x is a negative 27, or x is equal to 3. You have two solutions, but are they going to be do they work? If I take the 3 and plug it in, I'm fine. Over here, I'll be fine. But when I take the negative 27 and plug it into here, then the argument becomes negative. You cannot have a log of a negative number. So this is an extraneous solution. You have only one solution, x equals 3. One more quick example. What do I do if I have something that looks like this? My recommendation is when you have a radical, is you rewrite this as exponent form, which means I would rewrite this as the natural log of x plus 2 to the 1/2 power. And then I can use expansion rules and rewrite it with this 1/2 out in front. I want to isolate the log, so to get rid of the 1/2, I times both sides by 2, and I end up with the natural log of x plus 2 equals 2. Now I have an isolated log. Use the box circle triangle. E squared is x plus 2. So x is e squared minus 2. And you can plug that in, and it would work for you as your solution. You could also have left it, in which case it's already isolated, which means I can just use the box circle triangle right off the bat, and I would get e to the 1 is the square root of x plus 2. But because I haven't really showed you how to solve this, you might not know how to. But if you do, to undo a square root, you need to square both sides. And so you end up with e squared equals x plus 2. And so then x equals e squared minus 2. And you can see I get the same answer either way. Depends on what you're familiar with and what you know how to do. So we'll do more examples together in class. There you go.